think I need oh, there it is. So, does this work? Okay. First of all, I would like to thank the organizers for this conference for having such a wonderful conference in such a beautiful place. Also, I would like to thank them for inviting me to give a talk here. And also, I would like to thank the speakers who have given some amazing talks and very educational for me, at least. So I'm going to talk about 60 superconformal theories. So the progress on this subject, of course, starts from old works by a number of physicists. I'm listing here just a sample, and as well as some more recent works, which has intensified, I would say, in the past 3 or 4 years. Again, this is not a complete list, but it gives you a flavor of the people who have been involved in this area. So the plan for my talk is, first of all, to describe the motivation for studying 60 superconformal theories, and then study briefly or go back to the usual case, the simplest case, the 2,0 case, and its ADE classification. Then talk about 1,0 superconformal field theories and how they are classified via F-theory. I'll talk about some aspects of the anomaly polynomial in these theories and the A theorem, and properties of tensionless strings in these theories, how we go about computing the superconformal index. And then I talk about the extension of these ideas to little string theories, and briefly mention some ideas about compactification to lower dimensions, and then finish with some future directions for this. So why we study conformal theories perhaps doesn't need much motivation. As you all know, they are standalone quantum systems, and many applications. The original one perhaps is in the context of condensed matter physics, the critical phenomena. In the context of particle physics, people have tried to use this in ideas, even in phenomenological kind of setups. And of course, quantum gravity and the context of holography, these are very interesting to study. Now, the question arises whether we can actually classify them, and do they exist in arbitrary dimensions? Well, it's difficult to prove the existence and classification of non-trivial conformal field theories in higher dimensions. However, with the assumption of supersymmetry, things become much simpler as you go up in dimension. So supersymmetry serves as a very strong constraint in making things easy. So in fact, when you go up in dimension, things become easier and not more difficult. And the highest dimension for a conformal field theory to enjoy supersymmetry is 6 dimensions, as is done by the classification of NUM. And this is related to the fact that the conformal group in 6 dimension is SO6, 2, which relates to the Lie algebra of SO8, and this enjoys a triality symmetry. And the triality symmetry plays a crucial role for this to make sense. So it's really, in some sense, it's reminiscent of the structure of the type 2 strings, the existence of string theory, as crucially being related to the triality. These special conformal theories exist in some sense related to that same fact, and it's the highest dimension we can go. They're labeled by an n, which is the number of supersymmetries we can have. Now, there are 2 types of superconformal theories in 6D. Either n is 2, 0 or 1, 0. And I will explain why later. And what we know about them is that, well, we think they exist. That's number 1. The main argument is really based on string theory. And they involve tensionless strings as their basic ingredients. When you go to the conformal point, instead of getting light particles or massless particles, you get massless strings or tensionless strings. We have no Lagrangian formulation for any of them. So these are totally mysterious theories from that viewpoint. The 2, 0 case is classified by an ADE classification. The 1, 0 case has also been classified, we think, in terms of some generalized quivers, which are a bit more intricate. Many interesting conformal field theories in lower dimensions can be obtained by compactifying these theories on various different manifolds. So you start with 6D and you go down to these different, from different paths with different manifolds to lower dimensions, and you generate a huge list of conformal theories that way. In fact, you can also presumably break supersymmetry and obtain non-supersymmetric theories that way as well, even though most of the study has been done on the context of superconformal symmetry, preserving some supersymmetry. And conjecturally, in fact, it's possible that all lower dimensional CFDs can be obtained from these six-dimensional theories. We know that from the examples, we obtained a huge list, and perhaps all of them, we do not know. And the dualities in lower dimensions become geometric symmetries from the viewpoint of the six-dimensional theory. Depends on the choice of the manifold, and cut and paste of them will give you duality symmetries in lower dimension. So in a sense, the 60 superconformal theories could be in some way a mother of all CFDs and dualities in them. So understanding these theories is a basic key point for understanding all conformal theories, perhaps. Some basic algebraic results based on realization of unitarity and superconformal group. I'm going to be using abbreviated references. I hope you don't mind. If you go back to my talk, which will be on the website, you will probably be able to identify them by looking at the first page of my talk, which is who are the key people. There's some degeneracies on some letters. I apologize in advance. So the first thing is that OSP 6,2/n, which is a superconformal group in 6D, can only be realized with n equals to 1 and 2. And this is related to the existence of stress tensor. So that's number 1, or 0 in fact. Number 1 is the conformal fixed point has no moduli which preserve superconformal invariance. So there's no moduli space. That's easy. We don't have to study that. To go away from the conformal fixed point, we can only give VEV to fields. Usually in lower dimensions, we usually have two options. Either we give VEV or we add some operator to the action. Here, to go away, you only have one way to do it, and that's giving VEV to the operators. And there are two basic ways we can do that, by giving VEVs, which takes you on tensor branch, which is the analog of the Coulomb branch in 4 dimension, or the Higgs branch. The 2,0 theory has SO5R symmetry and has no global symmetries. The 1,0 theory has SU2R symmetry, and this SU2R symmetry continues to hold on the tensor branch. It can also have additional global symmetries. Okay, so those are some basic aspects of these theories. So we come to the first case, the 2,0 case. As we well know, these are believed to be classified by ADE, and the simplest string construction of the A case involves a very simple system. You take M5 branes, n coincident M5 branes, and we believe that the infrared limit of n coincident parallel M5 branes is a conformal theory, which is this 2,0 A class. And the conformal theory has no adjustable parameter as expected. There's a deformation away from the conformal point, which separates the M5 brane by giving expectation value to a scalar in the tensor multiplet. And there are M2 branes which are stretched between these M5 branes, give rise to strings on the boundaries whose tension is proportional to the distance between these M5 brane, which is the VEV of the scalar field. So evidence for their existence, well, one evidence is holographic realization via ADS 7 times S4. So that's a good news. More recent evidence is based on Bootstrap. And this group shows that if you look at the 2 and 3 point function of the energy momentum tensor, by the amount of symmetry for 2,0, that's uniquely fixed by some parameter, some number C, which depends on which case you're in, A or D or E. And there are various arguments what this C should be. It is in terms of the group properties like dual Coxeter number and so on. And they check this prediction for the particular case A1, and they find strong evidence that the Bootstrap actually gives you rise to the 2 point and 3 point function of the energy momentum tensor, predicting basically the C, the central chart, the C value for the A1 case. This is already a very interesting example where power of Bootstrap extends all the way up to 60 to the most supersymmetric theory, and this is very promising. The D and the E case cannot be realized naturally in M theory. Type 2B is more powerful for this. So we look at the infrared limit of type 2b on the singular locus, C2 mod gamma, where gamma is one of the discrete subgroups of SU2, and in this case we get A, D, and E. More precisely, this is actually gives rise to what's called little strings, but the particular limit of it we take will give rise to the also the superconformal fixed point. The blow-up of the ADE singularity, which corresponds to going down the tensor branch, gives size to the spheres, which are singular at the orbifold point. So the eighth case corresponds to the usual Dynkin diagram, and then you get, for the D and the E case, the usual Dynkin diagrams, where each sphere corresponds to blow-up of the singularity, whose size is controlled by a scalar in the tensor multiplet. We get strings by wrapping D3 branes. So we're in type 2b, so there are D3 branes. We can take the D3 brane, wrapping around the 2-sphere, so it gives you a one-dimensional string whose tension is proportional to the volume of the sphere, which is related to the expectation value of the scalar in the tensor multiplet. So as expected, you have some strings whose tension relates to the volume or the expectation value of the scalar. There's a duality between M-theory picture and type 2b. Basically, the picture looks like this. So if you take M5 branes, you stack them up next to each other. If you use the M-theory to type 2a to type 2b duality, so M-theory to type 2a converts these M5 branes to NS5 branes. And then you go to type 2a to type 2b, they converts the NS5 branes to tab-knot spaces. And the collection of tab-knot spaces stacked next to each other gives you these singularities in the type 2b language, which correspond to AN singularity. So the picture of branes is more or less the same picture as we draw by this chain of duality. Moreover, the M2 brane I told you about, which is stretched between M5 brane, giving you tensionless strings or light strings, in the M-theory language, converts in the type 2b language by the same chain of duality. M2 branes, the first step becomes D2 brane, and the next step becomes a D3 brane. And this is the same picture as we had before. Let me move on to 1, 0 superconformal field theories, which are more recently studied. Now, these have half as much supersymmetry, and they are classifiable. Even though we don't have a proof that they are classified, we think they are basically classified. The idea is based on realization of them via F-theory. So, and in some examples, I will mention some examples, they can also be constructed via M-theory, but not in the full generality. So in some large class of them, you can actually get them via M-theory, but not in all. And let me remind you what basic construction in F-theory is. So we want to go down to 6 dimensions. So to go down to 6 dimensions in F-theory, we need elliptic threefold, which in the type 2b means that we have a 2 complex dimensional base, and the elliptic fiber, which determines the coupling constant of type 2b, could potentially vary over the base, and it could have, in particular, singularities of elliptic fiber at some points. So let me go back to M-theory and give you some examples of how they look in the language of M-theory for these 1, 0 theories. The simplest class is the same we started with, the A class, M5 branes. But this time, instead of taking it in flat space, we just put them in the background of an ADE singularity. So this is not, so I hope this is not too confusing. There are 2 notions of ADE appearing here. One is in the notion of what are the M5 branes. So I called this AN before, or AN minus 1 before. But there's also the singularity they are probing. So the ADE here, which is yet a different ingredient. Notice that in M-theory, an ADE singularity appears on a codimension 4, which means in 7 dimensions. So this is a 7-dimensional locus, whereas M5 brane are 6-dimensional. So it leaves 1 dimension between them different. So you can place the M5 branes on the line of the ADE singularity. So you can study the theory where there are n M5 branes on this line, on the line of the ADE singularity, and if you bring them all together to one point, that corresponds to a conformal theory. Again, you get the usual strings as we discussed before, by taking M2 branes stretched between them, and similarly, if you go now to the type 2b, or more precisely in this context, you can do it in terms of F-theory, you have the M5 brane ingredient gives you the before you put any ADE singularity, as we discussed, the M5 brane gives you the AN singularity of type 2b, and putting the background of ADE gate singularities, ADE singularities corresponds to wrapping 7 branes in the type 2b language, where the type of the 7 branes will determine which kind of gate symmetry we get. For example, if you have E-type, you have to put E-type 7 branes, and you get some kind of matter between them and some kind of gate symmetries which are punctuated by the presence of these M5 branes. The same story with the D3 branes, again wrapping them, but now they are more interesting because they interact also with the 7 brane, which is wrapping the same sphere. So you get more interesting structure for these strings. Another example you could study are the M5 branes at the Hojava-Witten wall. So you take an M5 brane near the wall, and in the F-theory picture, these points are corresponds to, again, the same points in the M5 brane, in the type 2b tab-knot geometry. But then it turns out that the point of the M5 brane near the wall, instead of giving rise to a sphere with the usual sphere, you get a sphere which I've labeled here by 1. And what does that mean? Well, in the context of the AN singularity, the spheres, for example, for the A1 singularity is cotangent of P1, which means the normal bundle is the O-2 bundle. So the number 2 here just refers to that fact, that's the cotangent of P1. So these two are cotangent of P1 because these are the same geometry as we had before, but the sphere that you get in this case, the last one, turns out not to be the cotangent of P1. Instead of an O-2 bundle, it's the O-1 bundle. O-1 bundle does not give you something which is Ricci flat. So that if you naively took type 2b with an O-1 bundle on P1, that would be bad. It would break supersymmetry. However, that is not a problem in the F-theory context, because what happens is that the elliptic fibration is non-trivial over the O-1. The elliptic fibration can be taken to be trivial over the other ones, which means the coupling constant of type 2b can be taken to be constant. But over the O-1, it cannot be taken to be constant, and it will have, in particular, generically 12 points, which it degenerates. And so, as I said, these are the normal bundles for the geometry. So the elliptic fibration, if you want to draw it, it will look like this. It's constant, basically most of the area, except over this, it singularizes over these fixed points. The total geometry of O-1 bundle over P1 gives rise to half K3. Instead of having 24 singular points of the elliptic fibration, we get 12, which is the reason it's called half of K3. Another class of examples we can study in the context of F-theory is the following. You take the base to be just the C2, and the elliptic fiber just the constant T2, but now you take a special complex structure for T2, which admits extra Zn symmetries. So in this context, you can take some nth root, so suppose alpha has some nth root of unity, alpha to the n is 1, and assume that alpha to the minus 2 is a symmetry of T2, which means not all the n's are allowed, because the symmetries of T2 are either Z2, Z3, Z4, or Z6, which gives rise to the numbers 2, 3, 4, 6, 8, and 12 to n. The reason you get these 12 is, remember, this is squared. So you get squared, so therefore the degrees are fine, and these will be symmetries of T2. So you take this geometry and you mod out by this orbifold with this Zn action. The determinant of this is 1, so it's supersymmetric. It's a Calabi-Yau geometry. And in fact, this is reminiscent of recent constructions of n equals to 3 theories in 4D, where you take, basically you put one more alpha inverse here, you get a Calabi-Yau fourfold version, alpha, 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 or alpha inverse, alpha, alpha, alpha inverse, and then you put a D3 brane probing it, and this gives rise to n equal to 3 class. So this is somehow like the 60 avatars of similar constructions in 4D. But here we don't put any D3 brane, this is just the geometry itself. We just take this geometry in 6D. And if you look at what this, if you look at just the base of the F theory, it's just this C times Z mod out by Zn. If you look at what that means, the fixed point corresponds to a geometry which, if you blow up, gives you an O-n bundle over P1. So this simple construction gives you, for the Z2 case, the familiar cotangent of P1. But for the other cases, it gives you new examples of would-be conformal theories, labeled from all the way from 2 to 12. But you don't get all the numbers, you don't get 5 or 7 or so on, but you get a bunch of these numbers from this simple construction. Notice that the action on the C2 is not in SU2, but in U2. So if I looked at, in general, except for the n equal to 2 case, for all the other ones, this is not a subgroup of SU2, unlike the ADE case. So it turns out that if you do this construction, you find that for the O minus n over P1 case, the construction I just told you, for when n is bigger than 2, you necessarily have some kind of thing going on as a brane or 7 brane on the P1. So you have non-trivial gate symmetry automatically forced on you. And these are the least amount of gate symmetries you will get. The least amount of gate symmetries that you will get for them will be these. Now here I have also included a few cases that was not in the previous one, 5 and 7, where you can actually do the similar construction in F theory, but they are not orbifolds in the same simple form, but there are some kind of generalized versions of them. Now all the known examples of 2, 0 and 1, 0 can be realized in F theory from this kind of picture, which motivated the basic classification idea. So we classify all the possible bases that can appear in F theory up to blow-ups. So what is a blow-up? So I have to clarify this. So I gave you the example for the O minus 1 theory, this one. This one actually, if you shrink it down to 0 size, it leaves no imprint on the two-dimensional space. Unlike the A1 singularity where there's a singular point, if you shrink this guy, you actually cannot detect it. The only way you can detect it is if you keep track of the elliptic fibration where something is there. So there is something going on, but you have to keep track of the elliptic fiber. So if you just look at the base, you don't detect it, and that's, you take a point in the base of the F theory and you blow it up. This is the blow up of a point, which is non-singular. This gives you rise to the curve, which is 1. This is a very exceptional situation here, and the fact that it's next to this wall means that it's going to enjoy the E8 gate symmetry, which lives on the Ojava-Witten wall, as a global symmetry. So this O minus 1 theory will have a global symmetry, and it's a very important basic ingredient in these theories. So the idea for the classification is to first study all the possible bases which allows this minus 1 curves to all be shrunk down. So shrink everything you can, that means the minus 1 curves, and see what you end up with, and classify all of those. And it turns out once you do that, all of them can be written in terms of 2 complex dimensions, mod out by some discrete subgroup of U2 instead of SU2, but not arbitrary subgroups of U2 arise. Some specific subgroups arise. Of course, the ADE is a special subspace of this, subcase of this. These are what we can call endpoints. That means when you blow everything down that you can. And then you have to get the non-singular geometry to know where things were, you have to blow up as much as you can in order to avoid having singularity. And this basically introduces these minus 1 theories as gluing or building blocks between these singular geometries. So these are the blow-ups to get rid of the singularities. And each one of them will be surrounded by these other things, which can have, in particular, some symmetries on them, gate symmetries, G left and G right, which should sit inside the E8 because that's the global symmetry of the O minus 1 theory. So from the perspective of this O minus 1 theory, you can think of connecting to these other nearby nodes simply means you're gauging a G left times G right symmetry of the E8 global symmetry on that theory. That's a gauge theory interpretation of what you're doing. So there's some M theory examples. So if you take M theory interpretation, let's consider M5 brane probing D and E singularities. For example, let me just give you one example. Say you have 2 M5 branes probing the E7 singularity in M theory. And it turns out an amazing thing happens. The M5 brane now splits up. And this splitting up is mirrored in the F theory language by understanding what are the geometry of this blow-up symmetry. So we understood this from the blow-up perspective, from exactly what kind of P1s can appear with what kind of gate symmetries. And so this is basically fractionalization of M5 brane probing the E7 singularity to different pieces. So the E7 I was just talking about, where it had these groups, comes from gluing up, having these particular glue theories, these one theories, next to some of the other more basic building blocks. And so we get this kind of chain. If you do the same thing for SO8 or some other groups, you get some different kinds of chains here. For E6, you get this chain and so on. So this is as far as some general examples, but it gives us rise to this pattern that if you want to have M5 brane probing E6 singularity, we could call that morally an E6 times E6 bifundamental, so to speak. If it were the A case, and you put an M5 brane, you get a bifundamental matter in the SUN times SUN bar representation. Here, the same thing happens, but now it's not just the regular matter representation, but a conformal system. So M5 brane probing E6 singularity gives rise to a conformal theory, which has, if you blow up, it has three scalar fields corresponding to the tensor branches, which correspond to the O-1, O-3, and the O-1 curves. And if you do the same thing with E7 and E8, you get some similar picture. So these pictures we understand from the perspective of F theory, and there's no easy explanation, easy simple understanding in the M theory language. But it also leads to the basic building blocks, which is called the non-Higgsable clusters, which is the following. So this is basically the beginning of the classification program more systematically. Namely, what are the, if you start with the superconformal theory with 1, 0, and go on the tensor branch, what are these spheres? What are these kind of self-intersections that you can get? Well, the basic building blocks in the F theory you can show is made up of a single sphere with an integer n going from 3 up to 12. We saw examples of this in the example I showed you as an orbifold. But then there are also the other ones. There's three other exceptional cases involve the O-3 and O-2 curves. So there are three exceptional cases like this. And in addition, you of course have the usual ADE case that we had before. So we use these as our building block, pieces of Legos, and then the only rule we have to glue them is to use this O-1 theory. So that's the only allowed way to glue them together. So you use these as what are these called non-Higgsable clusters, you use them and you connect them via this O-1 theory. Now, if you just connect them, you cannot connect them arbitrarily. The intersection matrix that you get from this, like the corresponding Dynkin diagram that you get, has an intersection matrix. It has to be, depending how you read it, either positive definite or negative definite. Depends on whether you think about O-2 as a -2 in the diagonal or +2. So let me just use here terminology positive for now. So this is related to the kinetic terms for the scalars being positive definite. And they are not allowed to form loops. Now, if you try to connect to loops, you can in principle get a positive definite matrix, but the problem is you cannot embed this in F theory. So the F theory construction tells you it is only made of trees. So you're supposed to make of trees and use these basic building blocks, and you can use O-1 curves to connect them, and you have to make sure that the matrix that you get is positive definite. That's it. You have to classify this. And so it's beginning to sound not too difficult. It looks like some algebra problem. And it turns out that it is possible to do this, but it's helpful to actually introduce a terminology for me to say what the answer looks like. So it's useful to divide these non-Higgsable clusters to two groups, the D and the E type. By that I mean, remember there was these the O-n theories, which were 2, 3, 4, 5, 6, etc., which have some gauge groups on top of them, the minimal gauge groups they could have. So if they have D or E gauge groups, SO8 or E, I call it DE type. Or if you had the lower ones, 1, 2, 3, or 2, 3, or 2, 3, 2, or 2, 2, 3, and 5, these don't have DE gauge symmetry. So I will separate these building blocks with these pieces. This is, of course, the gluing guy, which I use to glue things together. And then there's this terminology for these I's, which correspond to this, the analog of the 1, 2, 2, 2 theory, which corresponds to n M5 brane probing the Hojava-Witten wall. So that's another kind of a notation I'm going to introduce, depending on how many M5 branes are next to the wall. So these are some of the basic ingredients. And so we introduce a generalized kind of a quiver where, which looks like this. We have DE type curves. These are depending on which one of them we choose, This is we have a label for the group. And then we connect them with some links. But these links are complicated combinations of the non-DE type building blocks. So it could be made of 1 or 2 to 3 or 5 and so on. So when I talk about the line, this line could be this collection, for example. So it's not just a simple bifundamental we are used to, but it's a generalized notion of such things. So it will have some kind of links of this type. So the final answer is that when you try to find what are the possible things that you end up on the tensor branch, you get something which looks like usual Lincoln diagrams that we are familiar with. Namely, there you can get typically a long chain. So the tree is not too unwieldy, in other words. It could have, a priori, you might have thought this could be a very unwieldy problem, but the answer turns out to be relatively simple. Generically, it's just a long chain, but it could have some decorations at the end, where these are those DE-type nodes, and these are the non-DE-type links made of all these different things. The groups that live on these guys have some interesting increasing structure. They embed into one another until the highest one, and then it stays there and then comes back, potentially. And these end nodes have some special features on what special things can happen. One can classify, and it's been classified, what are these end types. So you can recognize, of course, in this end story, the usual affine ADE is of this type too. So the usual ADE is also of this type. You have A, and the D and E have some extra things going on the boundaries. So here it's some kind of a generalization of AD diagrams. So there's some details here I'm sparing you, but one has to actually go about and classify exactly what are the possibilities, and it's a bit long list, but you can actually classify them. And here are some statements. And for example, these last two nodes that you can have, if there's more than one of these end things at the end, the one before the last one should be just a bunch of M5 brane probing Dojava involved. That's these ILs or AMs or INs, but the rest of them could be non-minimal decorations. So this is all classified, and then, so this is classified as the base, and then you have to put gauge groups on them. So you have to put 7 branes on them, and that's easy to classify because of the anomalies. The theory 1, 0 is chiral theory, and therefore anomaly plays a key role. So anomaly cancellation restrict what are the possible 7 branes that you can get, and this gives you decorations that you can put on top of this. So that's the basic classification in the F theory for these theories. Do these theories have dualities? That's a very natural question. Are any of these two theories that I described the same in disguise? We have actually evidence that there are no dualities in this theory. At least we couldn't find one. The obvious ones we thought there should be there weren't there. For example, if you take this geometry, 12, 1, 2. So this is a sphere with O minus 12 on it, and this is O minus 1 and O minus 2 here. And considering this is also 1, 12, 1. Both of these theories, if you blow down this 1 and then blow down this curve 2 becomes 1 and this 12 becomes 11, and if you blow down one more time, so if you blow down this twice, you get the curve O minus 10 over P1. If you blow down this also twice, you get O minus 10 over P1. Now, you might have thought that these therefore must be the same theories, because at the conformal point, you are supposed to shrink these anyhow. So what does it matter if this blue curve is on top of this blue curve or next to this one? You might have thought that since you're shrinking everything, at the end they're all the same. That's what we first thought, but actually anomaly computational, anomaly polynomial shows they are not the same theories. So there are no dualities we could find among any of these theories. And we conjecture that all these theories are inequivalent. There are no dualities in 6D. Now, anomaly polynomials that I mentioned is an important feature of these theories. As I said, these theories are chiral, and you can couple them to gravity background, and also you can turn on an SU2 R symmetry background. And this gives rise to the anomaly polynomial, which lives in 2 higher dimensions. It's an 8 form. It's a polynomial of this form. So here, just to give you the notation, the C2 denotes the second Chern class for this SU2 bundle. And the P1 and P2 are the Pontryagin classes for the tangent bundle. And so the anomaly polynomial is a polynomial which is determined by 4 coefficients of this polynomial. And the coefficients of the anomaly has been determined systematically for these covert theories that I mentioned. So if you start with these covert theories, there's an algorithm that you can actually use to compute what these alpha, beta, gamma, and delta are for these theories. You can then talk about RG flows and the analog of the A theorem for these 6-dimensional theories. So the analog of the C theorem in 2 dimension has a generalization called A theorem, which has been proposed a while back, which basically, in even dimensions, you take the expectation value of the energy momentum, trace of the energy momentum tensor, and there's a term proportional to the Euler class times some coefficient, and this A is the A function associated to the conformal theory. It's believed that A is positive and decreases along the RG flow. There's no proof of this in 6D, unlike in 2D and 4D for supersymmetric theories. One can expect A to be related to anomaly polynomials. So in the 6D, we don't have a clear understanding of why this object is a good C function or A function. Why does it decrease over RG flow? But unlike the lower dimensional case where we have a better understanding. But just as in 2D and 4D, for supersymmetric theories, A is related to the corresponding anomaly polynomials, and you might think the same is true here, and it is. So based on various consistency argument, it was proposed that for superconformal theories, the 6D-A function could be computed using the anomaly polynomial. As I mentioned, the anomaly polynomial is captured by 4 coefficients, alpha, beta, gamma, and delta, and very specific combinations of them, actually perhaps surprisingly simple combination of them, gives you the A function. And they checked, and also there were further checks that showed that this A decreases along the RG flow by using this picture from the F theory. So this seems to be a good candidate for the capturing the RG flow, monotonicity of the RG flow. So I want to now move on to a basic ingredient of these theories, which are tensionless strings. So as I said, these theories do not have a Lagrangian formulation because, and we don't expect them. And one basic reason for that is that tensionless strings play a key role. Well, you might have thought that, well, strings we are familiar with, and you might have something like a string field theory or something like that. So why not try something like that? So perhaps it's useful to contrast the fundamental strings with these 6D strings that you're getting to just get a base point comparison. So first of all, fundamental strings have a finite tension. There's no point in which they are tensionless. Whereas 6D strings can have finite tension or zero tension at finite distance. You can change the parameters in your theory and you get to zero tension. So that's one very basic difference with fundamental strings. These theories have, the fundamental strings of course has coupling constant. That's basically ingredient in trying to use perturbation series. There is no analog in 6D theories. There's no coupling constant. So that's not there. And so as far as quantization, we know there's an amazing fact about fundamental string which gives you Lorentz invariant spectrum in 10 dimensions and so on. And you might ask, what about if you try to do the same game with the 6D theories? Of course, the 6D strings, we know you cannot take fundamental strings and do quantization and get Lorentz invariant. That's going to have problems. But we know these theories exist, nevertheless. So there's no problem in trying to define it, but it's not going to be inconsistent with them not being a fundamental string. So for example, if you take BPS strings of the 6D theories, namely if you stretch it along a straight line, you can talk about what is the spectrum on this string stretch. And I will show you what are the methods to compute them. And you find it has SO4 invariant spectrum. But that's as expected because you're choosing a direction in space. You're breaking the SO5 symmetry by stretching the string. So we can actually do computations which only probe the SO4 part of SO5 rotation symmetry and everything is fine. But there's no notion of the more, so this is the thing we can actually compute is when it's a BPS string, when it's stretched straight. If you take it to be contractible, which is what we usually do in fundamental string, we do not know how to compute the spectrum or what properties the string has. So that's the analog of the question here. We don't even know how to address really in this context. The 6D strings gives rise to BPS states, and they enjoy 4,4 supersymmetry on their worksheet if you are doing 2,0 theories. And in the case of 1,0 theories, they enjoy 4,0 supersymmetry. one can check, one can ask what is this 2D system, supersymmetric system is. Well, you can use various arguments in string theory and dualities in some cases to figure out what the actual degrees of freedom of this theory are. At least in the infrared, you can figure out what does it flow to. And we can then compute the partition function of these strings. So these strings live in 6 dimensions. So you can take the 6-dimensional geometry to be a 2-dimensional torus times R4. And you can wrap the strings around T2. So then you have a partition function of the strings in T2. You have this R4. You can take a twisted bundle of R4 over T2. You can take R4 as you go along the various cycles of T2. You can wrap them around and rotate. As well as if you have extra symmetries like there are in the 4,4 case, you can also use the other R4, which is the transverse R4. You can also twist those along T2. And you can compute the supersymmetric partition function of these supersymmetric strings, supersymmetric tensionless strings, and they will, in other words, what is called the elliptic genus for these strings, with fugacities turned on, which corresponds to how these bundles, how these geometry is twisted as you go along the cycles of the torus. So you can compute these in some cases, and it can actually be used to compute the superconformal index. So there's a tension here, namely, to talk about these strings, you really have to go to Coulomb to tensor branch, which means that you have to separate the M5 branes or give way to the scalars in the tensor multiplet. And once you do that, you're away from the conformal fixed point. Nevertheless, the information about the dependence of the elliptic genus as a function of this scalar parameter can be used to compute the superconformal index of these theories. And the basic idea is that if you want to compute the superconformal index of these theories, you can take the geometry, which is S1 times S5 as usual. S5 can be viewed as this circle bundle over CP2. So if you think about this, this is like S1 times S1 over CP2. It's like a 2-dimensional torus over CP2, where this one of the circles is fibered over this CP2. So you have a T2 fibration over CP2. So if I draw this picture of CP2 as you're familiar perhaps in the context of toric geometries of CP2 or the PQ web branes of realization of the same picture, it looks like a picture like this. There are 3 corners. And you have the elliptic fibration, which is non-trivial inside, and over the corners, something happens. So you have a geometry near the corners, which are this, you can use the symmetries of CP2 to localize the computational superconformal index to come from these boundaries, the fixed points of the actions, which correspond to these corners. And at each corner, the geometry basically looks like a 2-dimensional torus times R4, somehow fibered over this. And this computation is basically boils down to the elliptic genus computation. Namely, you're trying to compute the partition function of the 1,0 theory in this background. What can it contribute to this? Only supersymmetric contributions can be there. But the only kind of object which is supersymmetric is the corresponding tensionless strings. So that's precisely the computation I was just telling you we can do. So you get from each of the corners the corresponding elliptic genus. And it turns out combining these and the localization will tell you have to integrate over the corresponding tensor branch, that parameter phi, to get the actual answer. So there's an actual product of 3 of these factors with some parameters integrated. So it's not the trivial objects, but you can actually formally compute it. And people have extracted first few coefficients of the index, but a closed formula for it does not exist. It's very complicated, but morally it's computable in this way. The 2D case, the 2D 4,0 supersymmetry for the 1,0 theories, for example, I'll give you an example of how these theories look like. So take M5 branes probing A singularity, A-type singularity. This is a 1,0 theory. And so you have M5, you can ask what does the strings look like here. You have a bunch of nodes here, and you can wrap the strings. You can have strings corresponding to D3 branes wrapped around each one of them multiple times. So there are different integers here labeling how many times you're wrapping the corresponding D3 brane. So the string is labeled by a bunch of integers, a vector of integers in other words, and you get some kind of a 4,0 theory with some multiplets here I don't want to bother you with. You can write down the corresponding 4,0 theory. Similarly, for the case of O-1 theory, which is the M5 brane probing the wall, you have the strings corresponding tensor strings, or the strings that you get, they are called E strings because the theory enjoys the exceptional symmetry E8. So you can write the theory for those strings. They should have an E8 global symmetry in them. And it turns out the theory is very simple, it turns out. It is just an ON gauge symmetry with some particular multiplet, Fermi multiplet, and some symmetric matter multiplet. And just to give you an idea here of how this looks like, let's do the case n equals to 1. So in other words, a single E string. A single E string is an O1 gauge symmetry of 16 fermions, which means a Z2 orbifold of 16 fermions, and that's the heterotic construction of the E8. So the fact that there is an E8 symmetry is not manifest here, just like it's not manifest in the E8 cross E8 heterotic string, and this happens to be the first of these E strings. The n equal to 2 and the higher ones are the higher versions of these. So it's an interesting generalization of half of the heterotic string, so to speak, the E8 part, so to speak, one of them. And there's the n-dimensional generalization, which means how many of these E strings you have. You might wonder whether the two E strings looks like two copies of the one E string. In other words, does the O2 theory get related to O1 theories in a simple product fashion? And the answer is surprisingly no. Unlike the fundamental strings, when two of these strings behave like two copies of one, just by reparameterization or putting them next to each other, this is not the case for these strings. So the partition function for two of these guys, the elliptic genus of them, is not equal to the naive answer one might have written down for fundamental strings, which just means that these strings bind with each other, not the same way that the fundamental strings don't. So it's the new bound states that appear here, which are different from what the fundamental string does. There are interesting probe strings for these theories, which are classified. So in a gauge theory, in 4D, you sometimes put Wilson lines. So you put massive particles, Wilson lines, and you ask about them, and you think about them as order parameters for a gauge theory. These theories also have similar order parameters, but in this case, instead of particles, you have order parameters associated with strings. And they are classified, the allowed charges that these probe strings can have are classified by the dual lattice to the Dynkin lattice I showed you. The quadratic form that I told you gives you natural lattice. The dual lattice to that, modulo the original lattice, gives you the allowed charges of these strings. This is familiar, for example, for gauge theories, that if you take, for example, SUN, so the weight lattice of SUN mod out by the root lattice is Zn, that's the anality, and it's the statement that if you have SUN gauge theory, you can use various representation of anality as probes of these theories. These theories also have similar story where you just use the Dynkin diagram I showed you, take the dual of it and divide by lambda, and that gives you the charges that you can use for probing these theories. And you can view them in terms of the type 2b construction. These correspond to non-compact D3 branes. So you take cycles. So I talked about spheres, which are compact, and you wrap D3 branes around them. Those give you the dynamical strings in the theory. But then you can take non-compact two cycles, which intersect these strings, and these are in dual lattice, and you take away the parts that screened by the dynamical strings, and you're left with the other string that we mentioned. Now, so far I've been talking about superconformal field theories. I want to digress a little bit because it turns out there's an interesting story having to do with little string theories, and the more we study these conformal theories, the more we feel that you cannot ignore the little string theory component of it. So it's not quite it's not quite right to ignore the little string theories and view conformal theories by themselves, because they're a very interesting interrelationship between them. So that's why I'm going to talk about little strings as well. But already this has been talked by two talks here, one by Mina, and also in the Gong Show by my student Tom Rudelius, who, by the way, is graduating this year and has done fantastic work. So I'm not going to talk too much about the little strings, but because in particular the parts I'm going to talk about mostly has been covered by Tom, but maybe I'll just talk about some highlights of it. So you can view these as certain limits of string theory where fundamental strings are still in the game, but gravity decouples. So one example is if you take M5 brane where you have M theory would have a circle, and you take a small circle, a tiny circle, and take the limit as you have a tiny circle, and you put M5 branes next to each other. That gives rise in a certain limit to what these little string theories are. And the nice thing about them is that you can have some kind of a string remnant having in that context. They are non-local, just like string theory is. The energy-moment tensor is not local. There's no local energy-moment tensor in these theories. But they have decoupled gravity. So there are some baby versions of string theory. But in some sense, they are like in gauge theories, we do asymptotic free theories, which have some scale in them. And we do conformal theories. So these are like the asymptotic free theories, which are good theories. They are not conformal, but they are good. And these are like that. So you can think about these little string theories very much like what you would think in terms of asymptotic free theories. They have some scale in them, which relates to the tension of these strings. So the difference here is now, I had previously in the superconformal case, we had this lattice of the charges of the strings, which form a definite lattice, positive or negative, depending on your convention. For the little strings, they are semi-definite. And it turns out they can have, in fact, exactly one null direction. And the null direction corresponds to the non-dynamical tensor multiplet in these theories, which is the Vafa of the scalar of that non-dynamical tensor multiplet sets the scale of that string in this theory. In this case, unlike the superconformal case, which is only 1, 0, 2, 0 supersymmetry, you could also have in addition the 1, 1 supersymmetric case. And of course, you can flow down to conformal theory just by going to a lower and lower scale. And so in particular, you can think about this as part of a conformal theory by flowing down. So I will not describe too much detail about these, but just want to say that simple arguments of linear algebra will tell you that the dimension of the null space, when you want to make this positive semi-definite, is either 0 or 1. So therefore, when it is determined as 0, there's only one null direction. And you can start with various geometries and talk about them, but I think I won't have too much time. But the basic idea is that it looks like the same classification we talked about before, except that previously I was restricting to positive definite in intersection matrix, and now we'll have semi-definite. We have one null direction. And a simple example of them is, again, we use the same ingredients as we discussed before. And as Tom described, you get basically one extra node, which is roughly can be viewed as affinization of the theory, the null direction, so to speak, of this lattice. And so the affine AD is one set of examples, but you can have more examples, and Tom talked about them. One thing that he didn't get a chance to talk about, I will mention briefly, is that just like fundamental strings where there's T-duality, these theories, unlike the usual conformal theories, can enjoy T-duality. So if you compactify these on a circle, and you shrink the circle, you might think you're ending up with a 5D theory, but you come back to a 6D theory, just like string theory does. So these theories also have these similar properties. And the T-duality here has a beautiful geometric interpretation. It turns out that if you take the F theory realization, it's particularly clear, because if you have an F theory, if you take two of these theories, and you go down on a circle, you get a Calabi-Yam manifold downstairs in 5-dimensional, because by the duality, you end up with the 5D theory, which is M theory on the same Calabi-Yam threefold. But it could be that a given Calabi-Yam three-fourths has two different elliptic vibrations. So you could choose one or the other. So therefore, you get two inequivalent 6D theories, which once you compactify in a circle, they become the same. And this is actually the way the T-duality works in these theories, the existence of double elliptic vibration in these theories. So again, I don't have too much time, so I will move on. An example of this is this. For example, if you take this one, which is affine A2, the T-dual of this turns out to be an SU3 with this geometry, gauge geometry on this one, which is in fact 1, 1 instead of 2, 0. There are other examples, and then there are some examples where it's self-T-dual. So some of these theories end up being T-dual to themselves. Now, let me briefly touch on compactification of these CFTs to lower dimensions. We can compactify them and get the interesting one. In 5D, compactification is particularly easy on a circle. Surprisingly, it hasn't been studied too much. The 4D has been most studied in the context of 2, 0, as we well know, in the context of the n equal to 2 supersymmetric theories. These Guyotto theories has been intensively studied, and you can study them even including punctures and this and that. The 1, 0 version of them has begun being studied. It's still at the primitive stage, but there's some progress. And there's much more interesting structure in the 1, 0 for these guys. I'll mention briefly in a second. Compactification of 3D has been undertaken in a number of papers. And also the 2D compactification has also been studied in a bunch of examples. So all these cases have led to interesting insights into these theories. So I cannot go over really details of them, except just tell you what the common themes are. The dualities in the lower dimensions are translated to geometric statements about cutting and pasting of the geometry. So in some sense, it's satisfactory explanation of dualities once we know these 6D theories exist. So that's why these 6D theories are fundamental to the study of dualities. The amount of supersymmetry adjusted can be changed by changing the compactification. And sometimes one can get some same lower dimensional theory from two different higher dimensional theories. So I'm being told I have zero time, so I will go very fast. Let me just say some things about at least compactification to 4D. So in the 4D case, as I mentioned, the 2, 0 case, if you do it on a genus 1, it already gives you the explanation of the Olive-Montanan duality by the SL2Z symmetry of the T2. Now, if you take the on a more general genus instead of genus 1, you can embed the SO2R symmetry inside the U1 of the U1 into the SO2R symmetry of the SO5, and this will give you the class S theories which Gayotto studied. And you can also do something which breaks it to n equals to 1 if you take the corresponding U1 holonomy and embed it in a different way into the SO5R symmetry. And this gives you an n equals to 1 theory, which has also been studied, interesting class of those. These theories all give you theories whose superconformal theory has moduli space of Riemann surface as part of the moduli parameter. For 1, 0 theories, the R symmetry is SU2, and so therefore there's not much choice. You have a unique choice. You just put U1 inside that SU2. And for genus 1, you get n equal to 2 theories, and higher genus, you get n equals to 1 theories. And one may think that this always leads to theories for which the superconformal field theory depends on a Riemann surface, but it turns out that's not true, that only some subset of the 1, 0 theories will give you 4D theories which depend on the moduli of a Riemann surface. For example, the O-3 theory has no such limit. And an interesting example of this which has been studied is if you have NM fibrils on a torus, NM fibril probing a G singularity, if you compactify that on a torus, you get a theory which corresponds to a class S theory with 2 full punctures and a bunch of simple punctures. And one can also study the same theory in a different way to take the limit, and you end up getting a NM5 brane probing G singularity by duality between M theory and type 2B translates to ND3 brane probing the G singularity, and by the Douglas-Moore construction we know we get the quiver theory in that case. So that same theory translates to these quiver theories in 4D. And it turns out the 61, 0 theories for which the moduli of Riemann surface plays the role as moduli is related to theories in 6D which have an AD orbifold singularity. So AD orbifold singularity in 6D is the hallmark of the 2, 0 theory. So the underlying mechanism for the moduli dependence of these theories is also the same mechanism for the 2, 0 theory depending on the moduli space. So for the NM5 brane probing the A class, nice interesting study has been done. In fact, I believe Shlomo Razamat is going to talk about this today in one of the parallel sessions. And one can also study the moduli space of the same theories on a genus G, and you end up getting the moduli space of pair of flat AD bundles on the Riemann surface or some abelian subspace thereof. And so let me conclude that I hope I have conveyed to you the rich structure of superconformal field theories in 6th dimension. A lot has been done, but many significant gaps remain. We have to complete the field theoretic reasoning for the classification. So the classification was motivated from F theory, and it looks a lot like a field theory argument in many ways, but it's not completely field theoretic. For example, some of the nodes, like O-1 theory, has no gauge group on it, so we cannot think about it in a conventional form, but it looks very much like it should have some kind of a different way of thinking about it, which actually gives you a complete classification. And, there's some issues having to do with the analog of what's called the O7 plus, orientable 7 plus with the plus sign, which the question is what kind of theories they lead to and what they correspond to in this classification. That a group of people are still studying, it's not conclusive. The algebraic meaning of the Dynkin diagrams, in my opinion, is probably the most interesting, mysterious aspect. We know that when you have ADE symmetries in 2, 0, in 5D we get ADE gate symmetry. What about these other Dynkin diagrams? What's the algebraic meaning of them? It's important to understand the string excitation. As I explained to you, we know some things about them, but there are a lot we don't know about them. Bootstrap methods are beginning to show power even in the 60 theories. And it would be very nice to develop this more effectively. And compactification to lower dimensions should give rise to a rich class of theories based on 1, 0 from 6D. So I will stop here. Thank you.
Maybe we have time for 1 or 2 pressing questions.
There's a question there.
Could you have U1 logo symmetry in 1, 0 as a T?
Well, you do get some subgroups of subgroups. Typically, you have SUN. You can choose U1 subgroups of them, but just the U1, I don't think so.
Are there any exclusions theorem?
Exclusion. I don't think there is any such thing. I do not know what the exclusion would be, but we don't have any specific one.
In what sense is this a complete classification?
Of F theory, from F theory side. Yeah, that's all. Because we do not know even for 2, 0, we don't have full classification.
Because it might mean that we're just looking under the lamppost.
Absolutely. So even for 2, 0, we could say the same.
And do you expect anything like that exists in higher dimensions without
The conformal theories, you mean? I don't. Well, so that's a good question. Whether or not 60 is the end of it, as far as conformal theories go. These lights don't have to be on this strongly. It's a lamppost principle, but I don't think this is necessary to illustrate the point.
You're on the spot.
Yeah, I'm this spot. Yeah, so it's a good point, Nadi. I don't think we have any techniques to study them. I think it'd be interesting to study. If I were to guess, I would expect them not to exist. But I mean, I might be wrong. It'd be interesting to study non-supersymmetric theories. If they do, of course, then these 60 theories will not be the ultimate mother of all conformal field theories. You can have other higher dimensional theories, and that'd be interesting to study. So I don't know about that. But it's tantalizing that it's not easy to come up with ideas of what do you do with them. How do you come up with constructions of conformal field theories with no supersymmetry? It's amazing that we do have this set thanks to supersymmetry and string theory, which can be robust. Actual classification is going to be very hard. And if we want to prove the classification, of course, we should start with 2, 0, which is already hard enough. There are some arguments towards an idea of classification. For example, going down one dimension and trying to argue you get a simply laced Lie group and so on. So there are some ideas there, but it's not quite a proof. But similar ideas may work for 1, 0, we don't know. But so the statement that these are full classification is, even in the context of F theory, we have to be careful. But I think more or less, in the context of F theory, this is a classification, and we suspect it may be a full classification, but we, of course, can't prove it.
Last question.
So, Copenhagen, for any type similarity, use macaque correspondence to get equivalence.
Yes.
This is that in this case.
This is what?
And this is a similar interaction example.
Well, there are orbifolds in these theories, but these orbifolds are not of the type that's perturbative string. So as I said, these theories can also be viewed as orbifolds. For example, some of them, the O-12 theory, for example, is a Z12 orbifold. But the corresponding theory cannot be viewed as a cover in the same sense. No, the answer to that is no.
So with that, let's
Thank you.